Hello all, and welcome as we continue on with semester 2. Just a heads up, the semester 1, all the guided notes are available in the course materials at the bottom of the classwork page, so if for any reason you want to go back and use those to study, look over, anything like that, those are available in the new semester 2 Google Classrooms. Now we're going to get started talking about limits, which will feel like a big review, but we're going to talk about a new way to deal with some types of limits that have what we're called indeterminate forms. So you're going to do this over the course of 2 days. This first problem set from 4.4 has a presentation number 10 here, and then you'll have a second problem set for the next lesson. Now, L'Hopital's rule is a specific rule to deal with some of these indeterminate forms. So for example, if we had this limit in the past, just as a reminder, the first thing that you always want to do with a limit is you want to just take the number that the limit's approaching, so in this case, -2, and just plug it in for the variable in the function and see what happens. So in this case, we end up with -2 plus 2 over -2 squared plus 3 times -2 plus 2, which equals 0 over 4 minus 6 plus 2, so we end up with 0 over 0. Now, 0 over 0 is not actually a number that you can do anything with, and that's because it's an indeterminate form, meaning that if we follow our rules that we understand for algebra, it could be different numbers. So it's 0 in the numerator, so it could be 0. It's the same number over itself, so that means it should be 1, but then dividing by 0 means it doesn't exist. And so because all of these different rules are affecting the same term, that's why we call it indeterminate, and we need to do something else. Most indeterminate forms are going to have to do with zeros and infinities. So we've got 0 over 0, plus or minus infinity over infinity, infinity minus infinity, 0 times infinity, and so on. Now, some things that have zeros and infinities in them are determinate. So like if I add two really big numbers together, we get a really big number. 0 to any power is still 0. And so on. So just because you see this doesn't mean it's indeterminate, but it's a good sign. And for this rule, which is called L'Hopital, it's a French word, that's why it looks like La Hospitals, but it's pronounced L'Hopital. There's two indeterminate forms you're interested in, which are 0 over 0 or plus or minus infinity over infinity. And the idea with that is that if you get one of these, such as 0 over 0 here, which is like, oh, okay, great, I could use L'Hopital's, that you can just take the limit of the fraction and go straight across with the derivatives. So we show that we're using L'Hopital's rule by putting an h over it, and then you're just taking the derivatives of the numerator and denominator, which will usually make the problem simpler. So for instance, in this case, I can use L'Hopital's. So I'm going to say that this is equal to the limit as x approaches -2, that number doesn't change. And then the derivative of the numerator and the denominator. And this isn't the quotient rule. It's just the derivative of, in this case, x plus 2 in the numerator and x squared plus 3x plus 2 in the denominator. And in these cases, you're just going to use the power rule. So limit as x approaches -2 stays the same. The derivative of x plus 2 is just 1. And then 2x plus 3 in the denominator. And with that derivative, I can plug this back in here. You end up with 1 over 2 times -2 plus 3 equals 1 over -4 plus 3 equals -1. So this is just a nice way to deal with some limits that in the past we would have had to do other things for. In this case, factoring could have worked, but we have ones here that sine of x doesn't factor. But it still has a limit, and we can find it. Again, we will start by making sure that we can use L'Hopital's, because you always want to make sure with that. Plug in 0 in this case for number 2. So sine of 0 over 0, sine of 0 is 0. So yep, we can use L'Hopital's. So then show that we're using L'Hopital's. The limit part stays the same. And then we just take the derivative of the numerator over the derivative of the denominator, like so. The derivative of sine of x as x approaches infinity, because we're still keeping the limit. The limit of sine of, the derivative of sine of x is cosine of x. The derivative in the denominator of x is 1. Plug this back in, cosine of 0 is equal to positive 1. Now, as you can imagine, because L'Hopital also has to do with infinity, that you will also see some limits with infinity. So, rules about that, remember, most functions either go towards positive infinity because they're growing without bound, or they go down without bound, so they go towards negative infinity. And this is true of most functions, unless there is a horizontal asymptote. And if you remember, horizontal asymptotes happen with rational functions, and they happen with exponential functions. But not all. So for example, here we have e to the x. It's got as it goes towards positive infinity, it goes towards infinity. And it does have a horizontal asymptote, but only as it goes towards negative infinity, where it goes towards 0. So this would be the limit as it goes towards positive infinity. This is the limit as it goes towards negative infinity. So even though it's exponential, it does have a horizontal asymptote, but not in that case. So when I plug in infinity for x, it's not like we're necessarily plugging it in, but it says, oh, well, this function is going to go towards infinity because it's going up like this. 2x minus 6 is a line, so it would also go upwards at the end. So that's, again, infinity. So we can use L'Hopital's here. So the limit as x approaches infinity, we keep that the same, of the derivative of each part. Again, we're not using the quotient rule, it's just the derivative of each part, e to the x, and 2x minus 6 is equal to the derivative of e to the x, as you recall, is just e to the x over 2. Now you can imagine if this was like x squared, there would be a 2x in the denominator. Same result would occur. You can just do L'Hopital's a couple times. There's no reason to say that you cannot use L'Hopital's rule several times until one of the functions no longer equals 0 or equals infinity. So in this case, when I plug infinity back in, I end up with infinity over 2. Dividing a huge number by 2 is still a huge number. So it is infinite, or you can say that the limit doesn't exist, and it increases without bound. So here's your introduction to L'Hopital's rule. You'll see another problem set tomorrow, just as a nice way to keep practicing that. Let me know if you have any questions on anything you've seen here or anything about transferring over to semester